Today, we're going to crack 3 classic linked list problems. But here's the thing. Forget about just memorizing code. We're going to unlock the fundamental logic behind these solutions so you can solve any similar problem that comes your way. Let's get right into it. And this right here, this is the core idea for everything we're about to cover. It's not about how fast you can type. Nope. The real skill is mastering how you manipulate pointers, those little arrows connecting our data, making them dance and switch in really clever ways to solve complex problems with beautifully efficient code.
All right, first up, we've got a problem that seems simple on the surface, but has this beautiful, almost mathematical solution, finding where 2 linked lists merge into one.
So here's the challenge for you. You're given 2 separate linked lists, but at some point, they join up. Your job? Find that exact intersection node. And here's the kicker. You can't use any extra memory like a hash set. So how would you do it?
The solution is this absolutely brilliant 2-pointer switch trick. Okay, imagine 2 runners, PA and PB, starting at the head of each list. When a runner gets to the end of their track, they don't stop. They jump over to the start of the other runner's track. And here's why that's so clever. It equalizes their total travel distance. By the time they meet, both will have run the exact same length, which guarantees they'll meet right at the intersection. It's awesome!
And this visual really breaks it down perfectly. You see pointer PA, it runs its list and then hops over to the start of list B. Pointer PB does the exact opposite. Because they both end up traveling their own unique part, plus the other list's unique part, they are guaranteed to collide right at the intersection. This switch just elegantly cancels out any difference in their starting lengths.
And you know what's crazy? The code itself is surprisingly simple. The real magic happens in basically one line. A check that says, hey, if my pointer hits the end, just jump to the head of the other list. That single instruction, that's what makes the whole thing tick, no matter what language you're using.
And yup, you see the exact same logic right here in Python. It doesn't matter if it's a fancy one-liner or a simple if-else block, the core principle of switching lists at the end is what makes it work.
All right, let's switch gears to our next challenge, and this one adds a major constraint. We need to check if a linked list is a palindrome, but here's the catch. We have to do it with constant, or O of 1, extra space.
So what does that mean? Well, it means the easy way out is off the table. Copying all the values into an array and using a simple 2-pointer check, nope. No cheating. We have to solve this by only manipulating the list itself.
And the way we do that is this fantastic 4-step dance. Step 1, we use that classic fast and slow pointer trick to find the middle of the list. Then, and this is the key move, we reverse the entire second half of the list right there in place. Now it's easy. We just compare the first half with our brand new reversed second half. If they match all the way, it's a palindrome. And finally, just to be a good citizen, we reverse that second half back again to restore the original list.
This little table really shows why this solution is just optimal. The time complexity is O of n, and honestly, you can't get better than that. You have to look at every node, right? But the real magic? O of 1 space. We solved a tough problem just by shuffling pointers around, without using a single bit of extra memory.
When you look at the C++ code, you see how this complex idea gets broken down into these neat little helper functions. One to find the middle, another to reverse a part of the list. It keeps the main logic super clean and easy to follow. Find mid, reverse, compare, restore. It's just a great example of smart modular design.
And no surprise, the Python version follows that same elegant modular structure. It just goes to show, good logic works everywhere.
Okay, for our final problem, we're going to rotate a linked list to the right. And you guessed it, this one has another clever trick up its sleeve.
So what does that even mean? Let's look at this example. You've got a list from 1 to 5. If we rotate it by 2, those last 2 nodes, the 4 and 5, just swing around to the front. Our job is to make that happen efficiently.
Okay, let's break this down because the logic is really cool. First, you walk the whole list to find out how long it is and where its tail is. Then, you do something that feels a little weird at first. You connect the tail's next pointer right back to the head. You literally make a circle. Once it's a circle, rotating is just about finding the right place to snip it.
So, where do we make the cut? Well, it all comes down to this simple formula. We use that modulo operator, k% length, just to handle cases where k is huge. The new head of our list is going to be length minus k% length steps in.
which means our new tail is the node right before that one, and that's where we break the link.
The C++ code makes this super clear. You see the line where we connect the tail back to the head? Poof, it's a circle. And then after we find our spot, we just set the new tail's next pointer to null. Snip. It's just 2 little pointer changes doing all the heavy lifting.
And the Python implementation? Just as direct. It uses that exact same circular strategy to get the job done efficiently.
So, let's step back and bring this all together. What's the one thing that connects all 3 of these solutions? It's not about some crazy, complex algorithm, right? It's all about clever, precise pointer control. I mean, just think about the techniques we've unlocked today. The 2-pointer switch to equalize path lengths. The fast and slow pointers to find a midpoint. Reversing a list in place without extra memory, and temporarily making a list into a circle to simplify rotation. These aren't just one-off party tricks. They are powerful, reusable techniques for your toolkit.
By understanding the why behind these techniques, you move beyond just memorizing solutions and into a much deeper level of problem solving. So the real question isn't just what you learned today, but what you'll be able to build with these skills tomorrow.